different response.
Hey, everybody, while we're waiting for people to arrive and to get started, maybe you could tell me a little bit about yourselves in an efficient way. Raise your hand if you are working in or interested in working in physics. Okay, raise your hand if you are working in or interested in working in philosophy. Okay. Are there CS people here? Okay. Math or maths people? Okay, good. All right. People interested in English literature? History? Good. All right, good crew. When do you want to get started? You ready?
Let me give you a second to introduce you.
Please do.
All right. Ladies and gentlemen, thank you very, very much for taking some time to be here. I know a lot of you, but I also don't know a lot of you. However, a lot of you probably know this guy, so I didn't really need to introduce him at this point. The man has gone viral several times, as a matter of fact, thanks to some of the talks we've done here, and also with Kurt Mungle and others, Sean Carroll. Whether you wanted that to happen or not is another thing. But at this point, I think, as a matter of fact, you're almost up to 500,000 views on one of your videos. So congratulations on that. It's officially viral.
Who needs an H index, right?
Exactly.
You also didn't see it on the news later today.
What did you do? Yes, we were checking out names. That was a good time. So I would say maybe just the shortest thing I could possibly say. Jacob, his name is now synonymous, I think, with philosophy and physics at Harvard. So we're very, very excited to have him here today. He is one of the kindest people I know, one of the smartest people I know, and I think we're going to have a really great time. So let him take it away.
Thank you, Miles. Thank you. It's really wonderful to be back here at Brown. I have a lot we're going to talk about today, so I'm going to get started. My name is Jacob Barandes. I work in philosophy and physics at Harvard. I will explain the relevance of this painting soon. Does anybody know this painting? Anyone know the name of it? Want to offer up the name? It's not Duchamp. Nope. David knows the answer already. So this is Magritte. This painting is The Treason or Treachery of Images. It's from 1929.
The bracket.
I'll explain that. Yeah, I've decorated the painting with the symbol of a ket. This is Dirac's 1939 bracket notation for reasons that will become clear later. Anyone know what the inscription on the painting says? Yeah, it says, "This is not a pipe." Now, he presented this painting and got a lot of criticism. People thought he was being oblique or esoteric. They didn't understand what he meant because, I mean, if you look at this, it's clearly a pipe. His reaction to people who criticized this inscription was, well, if it's a pipe, go ahead and stuff it. And people would say, well, obviously I can't stuff it. And he says, why not? I thought you said it was a pipe. And I said, no, it's a picture of a pipe. He's like, aha, it's not a pipe. It is a representation of a pipe. And you should not confuse matters of representation with matters of substance. Very important, especially given the time in the history of physics, the 1920s. All right, I'm going to move on. This thing periodically stops working for reasons I don't fully understand. All right, let's see if this works. Oh, good. Okay, we're working. All right, I'm going to begin with a little brief intro. I feel it's my obligation to talk about the philosophy of physics and in particular quantum foundations before we get moving. So quantum foundations is the study of the fundamental physical, philosophical, mathematical, interpretational, axiomatic structure of quantum theory itself. It's had a controversial and sociologically complicated history. There was rather famously a set of very important developments that happened toward the end of the era known as the old quantum theory from 1900 to the 1920s. That was a period of lots of heuristic formulas and guesswork. And then in the 1920s and 30s, modern quantum theory, as we now understand it, began to congeal. And there was a lot of work on what you'd call the foundations of quantum mechanics. people began talking about the measurement problem, the interpretational questions around quantum theory, questions related to causation, locality. But over time, these questions were often cast as trivial, already solved, a waste of time, a matter of merely failing to understand the theory correctly. You just don't understand quantum theory. That's why you're asking these questions. A symptom of lacking intellectual maturity. It's a sign of an intellectually mature physicist that we'd stop asking these questions. And although it sounds like I'm setting up a straw man, that's literally what Freeman Dyson wrote in an essay I assigned in my philosophy of quantum mechanics class. Or a mistake of taking things too literally. But I should say I have observed a positive generational shift in these attitudes, evidenced by the attendance of all of you at a seminar like this. So we're making progress. I need to say a few words about important spin-offs of quantum foundations, because I feel like it's important to justify the existence of this very small field and also argue that it should be better supported. Okay. So despite how few people have worked seriously on quantum foundations over the years, its negative career effects and its lack of funding, it's had an enviable track record of important spin-offs. Actually, before I begin, let me ask you a question. So I come from the Boston area. Let's consider the Boston area broadly construed, as philosophers like to say. So the very general Boston area, how many people work full-time at some kind of faculty level in the greater Boston area on quantum foundations? Think about how many universities are in the greater Boston area. How many would you say? Well, Ray knows the answer. Okay, that's not fair, but how many would you say? I mean, 20. I mean, think about how many string theorists there are at a given physics department, right? Or how many people working on early universe cosmology or so forth, okay? You could hardly argue that early universe cosmology has direct real world applications to this moment right now. Maybe spin-offs, sure. But in terms of like, how foundational is the branch of science, there are a lot. Brown has people working in all these areas. A lot of departments do. How many in quantum foundations? I heard 20. Someone else want to throw out a number?
1.
1. Okay. So the answer is around 3 or so. Why? Why is that? Why? That's, I think, a reasonable question to ask. Why? Right. So let me give you a little bit of an explanation of why I think there ought to be more funding and jobs in this field. Well, we have quantum foundations to thank for EPR states. I think all of you will grant that EPR is kind of important, even though a lot of physicists in the audience, you've all heard of EPR, right? Raise your hand if you've read the EPR paper. Shame. Just shame us. It's 4 pages. Entanglement quantum theory, Schrodinger's cat, 1935. Decoherence. Now, how many of you have heard of decoherence? Yeah, it's kind of important, isn't it? And a lot of people think decoherence was invented by Zurich because he sells himself as the guy who invented decoherence. He did not. Or Zay didn't invent decoherence. Decoherence goes back at least to David Bohm. If you don't believe me, this is David Bohm's 1951 quantum mechanics textbook. Chapter 22 of this textbook went in an unusual direction for textbooks. Quantum theory of the measurement process. And section 22.8 of this book is called Destruction of Interference in the Process of Measurement, in which Bohm laid out what we would now call the theory of decoherence. He brought this picture to Albert Einstein very excitedly, 1951, said, I think I've been able to resolve the measurement problem using this theory of decoherence that I've developed within the framework of ordinary, orthodox, or Copenhagen-ish quantum mechanics. Einstein was not persuaded. And by the end of those conversations, Bohm realized he had also not succeeded. Bohm recognized almost immediately that decoherence alone was not enough to solve the measurement problem, and he began work on his pilot wave hidden variables theory that year. The only acknowledgement he made at the end of those 2 papers was to Dr. Einstein. I think it's useful to note that Hugh Everett of the many worlds interpretation, Hugh Everett's long-form 1956 unpublished dissertation, all 137 wonderful pages from it, and I will be quoting from it at some point during this talk. His first 3 citations Of the approximately just 24 citations for the entire dissertation were all to Bohm, to his textbook and to Bohm's 2 papers on the pilot wave theory. He had read them all extensively, including chapter 22. So we have Bohm to thank for decoherence. And how was Bohm repaid for this contribution? Anyone know what happened to poor Bohm? Exile to Brazil. And his passport was taken from him and he was driven out of physics. Wonderful. Great track record. Good job. Wigner's friend thought experiment, which goes back to the first 4 pages of Everett's thesis, his long-form unpublished dissertation, and then was made more popular in a paper called Remarks on the Mind-Body Question by Eugene Wigner. It's now called Wigner's friend thought experiment, and we'll be coming back to that today. The Bell and more general Clauser, Horn, Chamonix inequalities from the 1960s and beyond. All of these people were told not to work on quantum foundations, career suicide. Bell used to tell people, anyone who came to him wanting to work on this, do you have a stable academic position? Otherwise, he would say, don't work with him. This is a travesty. It's an intellectual travesty. By the way, Nobel Prize, not 2022 for this work. The black hole information problem has yet to net a Nobel Prize. The no cloning theorem. In fact, Park's paper was, I believe, in the first issue of Foundations of Physics, a journal dedicated to quantum foundations. Dieks, by the way, who independently discovered the no cloning theorem in '82, rediscovered it along with Zurich and Wouters in philosophy of physics. Quantum contextuality, the Cauchy-Becker theorem, quantum advantage. So you know we're all excited about quantum computers. We think that maybe they can do things vastly more efficiently than any classical computer can do. That's called quantum advantage. The idea of quantum advantage goes back to a 1985 paper by David Deutsch, interestingly communicated by Roger Penrose. Fascinating. Okay, quantum theory, the Church-Turing principle of universal quantum computer, and he lays out, describing his theory of what he thinks quantum computers to do. But I want to call your attention to this, which was not unique in this paper. There were several references to this. The intuitive explanation of these properties places an intolerable strain on all interpretations of quantum theory other than Everett's. You see, Deutsch was motivated from some conversations he'd had, strategically arranged by, I believe, Wheeler and DeWitt for him to talk to Hugh Everett. Before Hugh Everett died, Deutsch was converted to Everettianism and was looking for a smoking gun argument that would convince people that the many worlds interpretation was true. If the many worlds interpretation was true, he thought we should be able to use the parallel universes for some purpose. And the idea of quantum advantage was born from that idea. This, he thought, would convince everybody that many worlds was true, because as he put it explicitly, if the calculations are not happening in the parallel universes, then where are they happening? He thought this would convince everybody that many worlds was true. So the genesis of the idea of quantum advantage comes from trying to convince people of a particular interpretation of quantum mechanics. Now, unfortunately for Deutsch, the other branches are not useful for quantum computing if they've fully decohered. And if they fully decohered, they have to be fully decohered to be parallel worlds. So insofar as they're possible worlds, they are in fact not useful for computing. So unfortunately, it doesn't quite work. And as he admits in the paper, you actually don't need to believe in the Everett interpretation. Once you've established this works, once you've been inspired by the Everett interpretation, any interpretation of quantum mechanics will certainly make the same predictions. So this is not quite the smoking gun that he thought. Nonetheless, clear evidence of an important spin-off of foundational work. Oh, wait, there's a page 3. Oh gosh, we have so little time and I can't get through all the spin-offs. There are just so many of them. Okay, the no communication, no signaling theorem, we will talk about that later. Quantum theory is a no signaling theory. It doesn't let observers send messages, explicit messages to each other about, to communicate signals and so forth. This is very important. Weak measurements, which have a complicated metaphysical status. I've written some papers on this. We can talk about that. Quantum circuit diagrams, GHZ states, the ellipse dividing bomb test for quantum causal models, and on and on and on and on. Considering its input to output ratio, which is essentially undefined. This is an enviable track record that I would stack up against any other area of physics. So again, I ask, why so little attention? Why so little funding? Interesting question. All right, we're going to move on to the meat of the talk. I'm going to start by talking about the axioms, because I want to lay everything on the table so no one can dance around and say, I don't believe that. We're going to get everybody's going to be on the table. Here we go. All right, let's start with wave functions. Schrödinger, 1936. Let Q be a label indicating some configuration in something like a classical-ish configuration space for a system at a time t. He introduces his wave function. So his wave function is a complex valued function of configuration and time. He was motivated by the Hamilton-Jacobi formulation of classical mechanics. He built this wave function out of the Hamilton-Jacobi function. He noted from the beginning that this wave function propagated not in physical space, but in configuration space. So if you pick up a copy of Griffiths' textbook, he says right at the beginning that the wave function is a field in space. It is not a field in space. It is in configuration space, as Schrödinger knew immediately on introducing this concept. In 1926, Max Born came along and decided that the best way to make sense of this wave function was that it's, well, he left out the mod squaring. In fact, he left this out altogether from the paper. It was in a footnote he added after the proving process, for which he ended up winning the Nobel Prize. But today we would say you mod square this complex value function, and it gives you the probability, or more properly, the probability density with which a measurement will obtain the outcome corresponding to the configuration Q at the time t. In 1926, Dirac interpreted this wave function as the components of a state vector in an abstract Hilbert space. This is Dirac's Brockett notation he introduced in 1939. And so what you do is you take the state vector and you imagine expanding it in a basis. And in that basis, the coefficients, the components, which you can also think of as being entries in an infinitely tall, technically in this case, continuously infinite column matrix, those entries are what the wave function just is, and the state vector is unit norm, capturing the idea that the probabilities all add up to 1. Okay? This is the state vector. Schrödinger and Dirac in 1926, well, Schrödinger introduced the wave equation in coordinate space, but Dirac generalized it to Hilbert space. For a system that is closed, whatever that means, the system evolves unitarily. There is some unitary operator u that goes from t naught to t. You multiply the state vector at the earlier time t naught, it gives you the state vector at the final time t. If the time indexed family of those unitaries is strongly continuous, then Stone's theorem ensures that there exists a generator, a self-adjoint operator H called a Hamiltonian. And in terms of that generator, we can write the time evolution in an incremental infinitesimal by infinitesimal moment in time differential equation. And this is the famous Schrödinger equation. Now I'm using Brown text for things that are nomological, law-like, for reasons that will be clear later, the things that express laws. Okay, I should say that this form of evolution is a special case of what von Neumann called process 2 evolution. Process 2 evolution, I'll explain in a little more detail what process 1 and process 2 are in a moment, but I want to just call your attention. This is an example of process 2 evolution. Smooth, deterministic in some sense at the level of the ingredients. It's process 2. Von Neumann and Landau, independently in 1927, introduced the concept of a density matrix. And those of you who've taken intro quantum or haven't seen intro quantum, you may not be familiar with this, but it's very important. In the simplest case, we have what's called a pure density matrix. That just means you know the state vector of the system. And if you know the state vector of the system, you compute its outer product. Outer product, that's column vector times row vector. And that actually is reverse matrix multiplication. It gives you an n by m matrix. And that matrix is called the density matrix. The density matrix, you can easily check, has trace 1. Now, this is in a case where you know the state vector of the system. But in the most general cases, if there's classical uncertainty about which state vector the system is in, or there's entanglement, which we'll talk about a little bit later, you can't actually write a density matrix of the system in this way. The density matrix, we say, is mixed in that case. It still has trace 1. It's still a positive semi-definite operator, but it does not factorize. And even worse, as Schrödinger pointed out in 1936, in the mixed case, not only is there no singled out state vector or wave function, there isn't even a singled out collection of state vectors or wave functions, because there is a continuous infinity of different ways to decompose a density matrix, each of which gives you different choices of state vectors. So this undermines in a very strong way the idea that wave functions are matters of substance. If in generic cases they simply fail to exist, then maybe we should be talking about density matrices as somehow more substantive than wave functions, but even that is a bit of a stretch. Arguably, wave functions are more a matter of representation than substance. Right. Proceeding, density matrices evolve under process 2 like this. This is still von Neumann process 2. You sandwich the density matrix between the unitary and its adjoint. Lerders proved in 1950, well, he took von Neumann's early musings and turned them into a rigorous statement about what was supposed to happen to a density matrix when an external observer conducted the measurement on the system. If you measure a true or false question represented by, in quantum mechanical terms, a projector or projection operator P, you're supposed to update the density matrix in this way. This is called a Lerders projection. The density matrix transitions suddenly in this way on a measurement by an observer of this proposition P. And this transition occurs with a stochastic Born probability given by that formula, which generalizes Born's original Born rule. This is process one evolution. It features a definite measurement outcome with an attendant probability associated with it, a measurement outcome probability. Okay, and I should say this formally resembles a Bayesian update. If you think of Bayes' theorem, it looks just like Bayes' theorem. In fact, you can think of projectors as kind of like generalizing certain kinds of conditional probabilities. And then the denominator is kind of the overall probability. You can think of this as Bayes' theorem, but it's got a P on both sides. In between that Greek letter rho, it's got a P on both sides because of the non-commutativity. You can sort of think of it that way. Okay, so now we're done. Let's now lay out the Dirac-Feynman axioms in one slide. A quantum system is represented by a density operator, and so forth. Closed systems evolve in this unitary way. You can generalize this a little bit to certain kinds of carefully prescribed open systems. A system is a collection of observables, A, B, C, represented by self-adjoint operators in the Hilbert space and their eigenvalues and possible measurement outcomes obtained by an external observer, whatever that means. The Born rule gives all measurement outcome probabilities according to that formula I gave you right there. You take the projector corresponding to the true or false question. Did this observable yield this result? Multiply it by the density matrix, take the trace, that's the probability. This generalizes Born's original formula. And immediately after an external observer's measurement, the quantum state collapses to lock in that specific measurement outcome. And this ensures that if any other observer, even if not the same observer, any other external observer comes along very quickly and does the same measurement again, before letting the system have any time to do any other kind of evolution, with almost 100% probability that second observer will get the same result as before. A couple things to say about this. The first axiom usually also includes some gluing rules, some mereological rules that explain how to define composite systems in terms of their component systems, and this involves tensor products. So just note I'm not including that because I can't fit it in the slide, then I wouldn't be able to tell you I had all the Dirac-Feynman axioms on one slide. This is process two again. Notice no probabilities stated in this second axiom, no singling out of a unique measurement outcome, even if you allow decoherence, which is what Bohm identified, right? Bohm noticed decoherence couldn't make probabilities or single outcomes show up. And so there's something lacking about process two compared with process one. Process one singles out a unique measurement with a specific probability. So that's it. These are the axioms. They're all on the slide. Here you go. This is what they should teach you the first day of quantum mechanics, but they don't, because if they taught you this, you would run for the hills and never come back. Instead, they're like, oh, it's okay. Quantum mechanics is just about waves. You like waves. Waves moving in physical space, because that's what the waves are, going through slits. They just tell you this so that they lull you into a state of stupefaction. Okay. There are problems we can see right away with these axioms. First of all, the measurement problem. What's a measurement? What counts as a measurement? What counts as an external observer? The axioms don't say. Without these definitions, there is just a manifest ambiguity in the demarcation between process one and process two evolution. How do we decide which process to use? Well, as I'd like to say, like the Supreme Court Justice Potter Stewart once said about obscenity in the Supreme Court case about obscenity. And obscenity, what is that? You know it when you see it. Maybe not the best way to think about physical theories. What's an external observer measurement? Oh, you know, you're in the lab, you do it. You know it when you see it. Okay, I think that's probably not very good. Okay, now there are some approaches that try to deal with this problem by dropping process one evolution altogether. That's the stochastic collapse postulate, and trying to derive it somehow from process two. But you can see this is going to be a huge lift, because process two is categorically different. There's no probabilities in process two. There's no singling out of outcomes. How do you get those things to occur from axioms that don't contain them? And this is a very difficult problem that arguably is one of the most interesting questions in a variety of approaches to quantum mechanics. So it's very difficult to do. There's another problem. I call this the category problem. The axioms only mention, in particular, measurements. That's the only phenomena they refer to. What about the presumably larger category of non-measurement phenomena that we think is happening all around us? I mean, you can't just stick brackets around something and say, well, it's an average now, and now it's an average of stuff just happening. This is basically chapter 6 of Shankar's book. Just stick brackets around it, and now these are just averages of stuff happening, whether there are people around or not. That's not supported or grounded in the axioms. The averages we get out of the axioms are averages over, you set up many, as best you can, identically prepared instantiations of your system, you measure each of them once, and you average the results. That's what the average is. These are not the same thing as just the average behavior of some unmeasured system, okay? And making that elision is a category error. It is the category problem. And so this is like a serious issue. What are astronomers doing with their telescopes? Are we really going to tell astronomers that when they look at a telescope and they're trying to understand the early universe, that they're actually mistaken? No. There was no measurements going on in the early universe. There was no measurements going on in the early universe. That's all that the quantum mechanics says is happening is measurements. So nothing was happening until you did the measurement of looking at your telescope. That's just wrong. I'm sorry. Now, can I give you a rigorous deductive argument that that is absolutely wrong? No. But some hypotheses, like the radically skeptical hypothesis, we just shouldn't entertain unless we absolutely have to, and arguably we don't. Okay. There are more. Oh gosh, there's more problems. What are the physical objects? What's the ontology? Ontology is the philosophy having to do with like what exists physically. What are the physical objects of nature here? Could wave functions and the Hilbert spaces they belong to be physical objects? We already had reasons to be skeptical about that. But there are more reasons, in addition to the fact that wave functions live in abstract high-dimensional spaces, which, by the way, was a reason why all the founders of quantum mechanics by the 1920s gave up the idea that wave functions were physical. The idea was resurrected by Bohm in 1951. And if you want to learn more about that, I have a paper on this, historical debates over the physical reality of the wave function. Bohm resurrected the idea, then Hugh Everett picked up Bohm's work and turned it into the many worlds of interpretation. But until the 50s, most people didn't think wave functions were physical. And I think there's still very good reasons to be doubtful. They're not invariant under a large class of gauge transformations introduced by Foldy and Wouthuizen in 1950. I will not have time to show you the technical details of this. You can talk about it in the Q&A if you want, but there's a broad class of gauge transformations under which all the usual objects of the Hilbert space picture fail to be gauge invariant. And in fact, this set of gauge transformations looks just like a non-abelian gauge group. And we're trained in physics, those of us who have physics training, to be very skeptical of non-gauge invariant objects under gauge transformations. Wave functions fail to be gauge invariant. And also there are somewhat more subtle theorems like Fell's theorem. This is a little bit in the weeds, but Fell's theorem argues that even an entire Hilbert space representation of a quantum system is fundamentally empirically undermined and underdetermined. That no finite number of experiments, no matter how big that finite number, can tell you exactly which Hilbert space representation you should be using, and therefore which objects you should be using. So it really seems these are not physical objects. There's been some recent work coming out of especially people working in quantum gravity at MIT to indicate that for closed universes, Hilbert spaces end up being one-dimensional. And given that we have no idea whether a universe is closed, and we shouldn't be able to infer this based on sitting in our armchairs, something seems to be going wrong because I don't know about you, but I don't live in a 1D Hilbert space, sorry. Now, there are further problems. There's one that I'm thinking a lot about lately, this question of mereology. What is the general non-contingent rule for the evolution of a generic open quantum system? If I give you a completely generic quantum system and it's open to its environment, how does it evolve? The axioms actually don't say. And so you might ask, well, then how do we do anything? And the answer is people wave their hands. They all make all kinds of special assumptions that aren't true in order to get the axioms to work. But it seems to me that the axioms should refer to at least one system that actually exists. I'm sorry, that's just me. I'm just a small town country philosopher of physics, but I think that should be true. There's a basic problem with open systems at the level of the dynamics of quantum theory that needs to be resolved. And I think this is actually an important target for work. Okay, but now I'm going to give you a thought experiment. I mentioned the Wigner's friend thought experiment that I think makes as clear as possible why the management problem in particular is such a severe issue. So this is due to Hugh Everett, popularized by Eugene Wigner, highlights the ambiguities in the axioms that arise from large systems. Let W be Wigner, an observer outside a perfectly sealed box. If you want, this box is a black hole, let's say. Okay. Inside the black hole or inside the black box is Wigner's friend. Wigner's friend is inside the box, and by agreement, Wigner's friend in the box is supposed to do a measurement of some quantum system represented by that very old-fashioned looking atom, also inside the box, say at noon. Right? Friend's supposed to do a measurement. Here's the question. Wigner, or us, outside the box, how do we model what's going on inside the box? Do we use process 1 evolution collapse, or do we use process 2 evolution because it's a closed system? What do we do? And if you're to say to yourself, well, I mean, this doesn't really matter or only applies to weird people who are sealed up inside of boxes, well, we could be in a black hole right now and not know about it. I mean, given the state of things, maybe aliens have decided that humanity is too dangerous to be allowed to exist. And there's a black hole, there's like a shell of radiation, a Kugelblitz of radiation, like converging on us. And it's already converged to within its terrestrial radius. So seen from the outside, we're already inside a black hole. And we don't even know about it. Then we're Wigner's friend. And we can't just say, well, people inside black boxes don't get to have outcomes. That doesn't make any sense. Okay. Now we're going to do my favorite flowchart, not just because I made it, but because I think this flowchart is the master flowchart of quantum foundation. Okay. So here's the question. We're modeling the interior of the box. Question 1, does the overall quantum state collapse or not? Now, if you don't believe there are quantum states or don't believe they're physical or believe quantum mechanics is wrong, your answer to this is no. So you answer yes if you believe that the relevant objects are well-defined and exist and that they collapse, okay? Well, let's suppose yes, you believe that in fact they collapse. Was it due to the friend's measurement? If you think it was, yes, then you're back to the Dirac-von Neumann axioms with all their attendant problems. If you think no, it was not due to the friend's measurement, well, then it was due to something else. And whatever that other thing is some dynamical mechanism. And now you're talking about a Girardi, Remini, Weber, or Penrose style or Weinberg style dynamical collapse theory, the GRW type theory. Bell also worked on some of these. Okay? The blue boxes, by the way, are terminal branches. That's where you stop. All right, suppose you say no for whatever reason. For whatever reason, you say no, you don't think the quantum state collapses. Is it still the case that the friend obtained a definite unique measurement outcome, at least according to anybody? Like, did that happen or did it not happen? If you believe, yes, it happened, that unique measurement outcome, because it is not reflected in the uncollapsed state vector, is something above and beyond the state vector. And the state vector either doesn't exist or is incomplete. And by definition, you now have what's called a hidden variables approach. And there are many hidden variables approaches. Some of them are more obvious, like the pilot wave theory. Some of them are a little bit more oblique, like the relational perspectival approaches. You believe people have their own personal wave functions and so forth. And in the Q&A, we can get into this because a lot of people see this box and they're like, I'm not sure that's a hidden variables approach. But here I'm speaking very broadly. Hidden variables approaches just say the wave function is in some sense incomplete. Maybe you say, no, there was not a unique outcome. Were there any outcomes at all? If you think there were any outcomes, but not a unique one, then you're saying something like a many worlds type approach, and then you have all kinds of problems trying to explain the appearance of probabilities and various things that are supposed to show up. If you say, no, there were no outcomes at all, or you refuse to answer, then you're talking about now anti-realism. You're saying there are no measurement outcomes. If there are no measurement outcomes, there's no empirical data, there's no empirical evidence. The theory is radically self-undermining. Now, before we go farther, let me just say, if you pick any other option than this one, you are acknowledging at the very least implicitly that there is some problem to be solved, like the measurement problem. The Dirac-von Neumann axioms need to be fixed. Because I see people say, oh, no, quantum mechanics is fine. I just don't think the Dirac-von Neumann axioms are correct. If you think that, you're already on my team, okay? This box, again, includes the possible case that you think that there's no quantum state or quantum theory is completely wrong. And finally, there is no retreat into mysticism or obscurantism allowed. Sometimes I'll give this talk and people will say, no. It's just that there's a superposition in the box. And you're like, okay, well, what do you mean? You can't say anything. It's just a superposition. And they'll just say that, and then that's the end of the conversation, right? That's not, I mean, if you just refuse to talk to somebody, that's one way to end a conversation. It's not a very polite way to end a conversation. We're going to be taking this box. I think this is the most promising box for all kinds of reasons. So some probability theory. Oh, and I should have said, by the way, and I shouldn't have thrown my hand, but all of you have to pick a box right now. These are all the boxes. How many pick the unmodified Dirac-von Neumann box? Go ahead, raise your hand. Good, great, thank you. Given that I've highlighted this box, okay? Dynamical collapse theory box. Who picks that box? No one ever picks that box. No one ever picks it. Okay, many worlds box. Couple people, yeah, okay, good. Anti-realism, nothing exists. What's the purpose of all of this? Why are we here? Okay, and hidden variables of some general kind. Okay, a bunch of hands didn't go up. I've been paying attention. Don't think I didn't notice. Okay, some probability theory. We'll also need to review how standalone probabilities and probabilities, all this stuff. Probability of proposition E, probability of proposition F. I call these standalone probabilities. Then we have joint probabilities, probabilities of the conjunction of two propositions, conditional probabilities. Hopefully people have seen conditional probabilities, the probability of E given F. Okay. Basically, it's just we fix F now and regard E as the variable, and we need to now renormalize. Divide in such a way that the new distribution for E alone is itself a probability distribution. That's one way to understand this formula. We can turn this formula around and regard it as a factorization of joint probabilities. Marginalization means that you sum over an exhaustive set of possible values of one proposition, and then what you're left over is the standalone probability of the other proposition. And if we combine this with a factorization, we get what's called the law of total probability, which looks a lot like matrix multiplication, interestingly. We take the conditional probability of E given Fi multiplied by the standalone probability of Fi and sum over I, and this gives us the probability of E. This will be important later. It is a linear relationship if we regard the adjustable quantities as the standalone probabilities and regard the fixed features of this as the conditional probabilities. It sets up a linear relationship. A random variable is a real valued quantity A, whose value depends on which proposition from a list is true. If E is true with probability P of E, then A has value AE. If F is true with probability PF, then A has value A of F. The expectation value of A is just its probabilistic average. We just multiply each possibility, which is random. It depends on a random event, a probabilistic proposition being true. We multiply each of the values of A by the corresponding probability with which it is true, and that summation is the formal expectation value of A, probabilistic average. More generally, if we have an exhaustive set of propositions, we define the average in this way. Crucially, we go out in the world, and if we're thinking of these as chancy probabilities, the way we measure expectation values is we set up a large number of n as best we can, identically prepared, independently distributed instantiations of our experiment. We measure the value of A on the kth experiment, A sub k. We add them all together and divide by n. This is in practice the discovery protocol, how we go and experimentally measure chancy, objective, probabilistic type averages. Nobody knows why this is true. It's one of the great mysteries of statistics and probability. And if you're like, oh, the law of large numbers explains it, sadly it does not. That's circular. And so statisticians will say that this is one of the great mysteries. Why does this work? Why does it get better as the number of trials grows? It's one of the great mysteries of probability theory. The set of all possible values that A can take on is called its spectrum across all the possible propositions, sigma of A. All right, suppose the standalone probability for proposition E sub I at time t is P E sub I at time t. And suppose the standalone probability for E sub j at another time t naught is P of E sub j t naught. And suppose we're given conditional probabilities that connect the two. And notice I'm putting these in brown because I'm going to think of these as like a law. Well, then for the law of total probability, we can project forward the standalone probability distribution at t naught to the standalone probability distribution at t in this way, with the conditional probabilities playing the role of a simple kind of dynamical law. Here I'm color coding all the e's. You can see all the e's match up. You can see where all the each sub j's match up. This is a simple form of time evolution, and it already looks a little bit like matrix multiplication. It is also linear, and that will be important later. All right, that's all the background. Now to get to the technical stuff. Indivisibility. What is indivisibility? Okay, well, let's motivate this with an appeal to a very familiar thought experiment. How many of you have seen the double slit experiment before? Yes, ubiquitous. Chapter 1 of Feynman Lectures of Physics, Volume 3. Okay. As Feynman said, all you need to know about quantum mechanics comes from this experiment. Let's take Feynman at his word, shall we? This talk is not limited to any particular system. I'm not saying we're only talking about double slit experiments in this talk, but it will be helpful to go through this single particle thought experiment to provide a good motivating example. I'm using red color coding to indicate things related to our particle. So in the double slit experiment, one imagines sending particles one at a time toward a wall with two slits, and then observing where the particles arrive on the screen. In every run of the experiment, there is one dot on the screen. One dot lands on the screen behind the two slits. Why do they do it with just one particle at a time? Why do you think they do this with just one particle at a time?
They don't want the particles to bounce on each other.
That's what they say. That's not the reason. Why do they do it with one particle at a time?
Then it goes random at first, and then you're like see the fate pattern.
That's a very good suggestion, and also probably part of the reason, but not the complete reason. You know why? Because it's so we can assume that we have a 3D configuration space where the wave function propagates. With one particle, a structureless point particle, its configurations are identified by 3 coordinates, x, y, z. And so you can confuse the configuration space with physical space. And you can tell students, oh, there's a wave, and the wave moves in 3-dimensional space through the 2 holes. That is, in fact, not the case. The wave function propagates in configuration space. And if you have 2 particles, that would be manifest. For 2 particles, the configuration space is 6-dimensional, because you need 6 coordinates to identify 2 particles. and try explaining to students, no, that's fine, intuitively, here's how it works. You have two particles. Now you just have to imagine a six-dimensional space, and the student's like, where are the holes? I don't know where the holes are in six-dimensional space. Anyway, okay? This is just basically to give students the sense they intuitively understand what's going on in the experiment, but it's actually very confusing, okay? So that's why they use one particle, so you can pretend that configuration space is ordinary physical space. Here's the setup. Splits are close together, but they're very much smaller than the distance they are together. Let's introduce some variables to indicate A, starting conditions, B, which slit it goes through, C, where it lands. Okay, now we're going to, and every run experiment, one particle goes through and lands at one location on the detection screen all the way on the right. Usually we assume that to get the conditional probability distribution, given initial condition A, which maybe we control very carefully, what is the distribution of probabilities for the landing site C? And usually what one assumes, sometimes implicitly if one is just working from Newtonian mechanics, which does have this property, one assumes that all you have to know is first figure out the conditional probability of what hole B it goes through, given the initial condition A, and then figure out the conditional probability given what hole it went through, where it lands, then multiply them together and then sum over B. I mean, this just looks obvious, right? And this is totally obvious. But of course, if you know about probability theory a little bit, you might be a little nervous here because this is not a theorem of probability theory. In probability theory, formally, that conditional probability P of C given B should really be P of C given A and B. That would make this a theorem. Dropping the dependence on A in that intermediate probability is a move, right? So this doesn't follow from just the general marginalization rules alone. It requires a Markov or divisibility assumption at B, and this is crucial. We make this assumption because Newtonian mechanics has this property. Anyway, if you do this, you get the following prediction. I mean, after all, if we're allowed to ask, did it go through the first hole or the second hole? If it went through the first hole, what would happen? We'd expect a Gaussian distribution, a bell curve. If it went through the second hole, we would expect a bell curve. And if we're allowed to use that formula, and we assume it's equally likely to go both ways, then we'll just get an even probabilistic mixture of the two bell curves. And we get a pattern of dots that looks like this. It's a blend of these two histograms. And then we get this shape. And indeed, this is what we find for macroscopic particles like stones. After all, stones do, to a very good approximation, evolve according to Newton's laws. Now, if we do this with electrons, one at a time, over many repetitions, we get a pattern like this, which is very weird and surprising. Now, if you plot the histogram, it looks like this, which looks a lot like wave interference. Now, you don't see a wave in a single experiment with one electron. You see one dot. But it does look a little bit like waviness. And so you might ask, does this mean each particle is somehow really a Schrodinger wave in configuration space, somehow reaching down into physical space, or that the particle somehow goes through both slits? Well, it does not require that, no. We'll show that you can account for this pattern merely by allowing the dynamics to be non-Markovian or divisible. If there is a discrepancy between these two expressions, I'll show later in the talk that when you compute this explicitly, you get interference terms. And in fact, if you do it for simple examples that you can do by hand, you get literally exactly the formula of interference, indicating interference is not some exotic quantum-only phenomenon, but is really situated in a broader context of any time you make an unjustified Markov assumption, maybe because you need to, maybe because it's too complicated to handle systems that are not Markovian. But every time you do that and you make an error, that error is just what interference is. Okay. Indivisibility is not making that assumption. And indivisibility is a simple and new idea. You can think of it as a failure of iterativeness of the laws. Notice we in the Markov case, we assume we can just iterate these conditional probabilities in a simple way. If that breaks down, you no longer have a divisible process. And once you start looking for indivisibility, you find it lots of places. It originated in the theory of quantum channels by Wolf and Chirac in 2008, I believe, in Communications and Mathematical Physics. The preprint was from 2006, a paper called Dividing Quantum Channels. But it was only applied to classical stochastic processes in 2021. That's like so recent that many of you were already old then. Usually I'm like, you know, hey, that Star Wars reference. And you're like, Star Wars? Oh yeah, my grandparents used to like that, okay? You, even like the first year college students are like, 2021, I was growing up by then, okay? This is like really, really recent. Simon Mills and Kevin Modi. And I talked to both of them, they're lovely people, and we had a lot of conversations about this. They did not think to apply these techniques to trying to understand quantum mechanics per se. The idea behind indivisibility is we've got some rule for dynamics, and I'll be a little more clear about what these rules are, where the rule just simply doesn't factorize in that way across time. So if you've got a rule, the Brown law from T naught to T prime on the right, and on the left, a rule from T naught to T. So you can start at T naught and end up at T prime or T. You may ask, does my physical theory supply me with a law that takes me from the intermediate time T prime to T that composes in this way? And if that breaks down, we say that we have an indivisible description. Yes. What's your name?
Kelly.
Hi, Kelly. It's nice to meet you.
So if are differentiable functions examples of divisible functions? So in the Schrodinger equation, because you were saying it's like a failure of iterativeness.
Yes.
So when we do things like, and you also mentioned this idea of iterativeness when you were talking to introduce the Schrodinger equation. So are these things related?
Very much so.
Okay.
Very much so. The kind of infinitesimal moment by infinitesimal moment
Yeah.
composability is necessary to get that differential equation, the Schrodinger equation, and that does break down here.
Okay, so would like trauterization also break down, like, sorry. So if you're doing, you have like the time evolution operator, and one way that people think about digital quantum computers, is I forget, it's the commutator approximation, I forget what that's called,
It's okay.
but.
What
yeah.
we'll see is that the purpose of the Hilbert space formalism is to restore a superficial semblance of divisibility.
Okay,
We'll end up with unitary evolution at the level of the Hilbert space.
okay,
But this is giving away the punchline of the talk, which is that what is the Hilbert space representation doing? It's letting you take theories like this, which are fundamentally not divisible, and giving you a representation of them where you have the mathematical tools of divisibility anyway, at the cost of a lot of exotica. Okay, so more precisely, this is a theory for which maybe this connective dynamical law doesn't exist. I should say that these theories are non-Markovian. They are, in a sense, generically non-Markovian of infinite order, but they require very little data to specify their laws, unlike a completely generic non-Markovian process. And once you start looking at them, you find them all over science. So I've been talking a lot with scientists in other areas, especially statisticians. Are there any statisticians here? Statisticians are wonderful. Wonderful. I wish I'd known more when I was in grad school. Just so curious and interesting and philosophical, and they're asking such deep, philosophically important questions, and they talk a lot to philosophers, especially epistemologists, even metaphysicians, about what is causation, what is causal discovery. It's a wonderful community. I adore statisticians now. Okay, so now let's talk about the proposal. Let's consider a particular theory, okay? This theory is going to be called the theory of an indivisible stochastic process. It's a non-instrumentalist, meaning I'm not just talking about observers anymore. This is now constructive type theory in Einstein's 1919 terminology. We're going to build the theory from raw ingredients. It does not put observers in some fundamental role. The process is going to be non-Markovian, and it's going to require the following data. The fixed ingredients of the theory, its ontology, its configurations, its laws, its mereology are going to consist of three basic postulates. The first postulate is about kinematics. This is what are the configurations, what is the ontology? Sample space, if you will. These are the possible arrangements of things. If we're modeling a system of particles, these are arrangements of particles in physical space. If we're talking about fields, these would be patterns of field intensities and polarizations in physical space. If we're talking about a discrete system, these could be on-off switches in their various configurations. That's the configuration space. The dynamics, this is the laws, the nomology. Nomology is the laws. It consists of a set of dynamical rules that map together pairs of times. Times T naught and times T. The times T naught are the conditioning times, the times T are the target times. These maps, for any pair T naught and T, they take in a configuration at the initial time and a configuration at the later time. That's the C cross C there, and map it to a conditional probability. And there's some collection of these maps, some sparse set of these maps. In general, little t alone, the target times can be on the continuum. There's no restriction there, but the T naughts are a little more limited. T naughts, which belong to that set capital T naught, are called division times. They correspond to what are called division events. And for a given one of these processes, there'll be some times you can condition on. Those are the division events, and other times you can't. The failure of your ability to condition on all times is the indivisibility. And so specifying the laws of this theory means that you specify these dynamical maps, these conditional probabilities that take you from certain kinds, certain initial times, conditioning times, to basically arbitrary target times. And you specify those become the laws, and they generically fail to iterate, and so they're not divisible. And finally, there's a mereological axiom that I can't fit on the slide. It's a little technical. This is just how we glue together component systems into composite systems. It's very analogous to Newton's third law. Newton's third law is, in fact, a mereological dynamical self-consistency condition. Mereology is the part of philosophy concerned with the part-hood relationship, components of things and composite things. I should have said it earlier. Newton's third law serves that role. Newton's third law says that internal forces cancel, and that cancellation of internal forces is crucial to the internal self-consistency of the laws of Newtonian mechanics. It means that whether we think of an object as one object or several objects, we get consistent predictions. That relies on the internal forces canceling. It's a very important ingredient. And there's a similar mereological dynamical self-consistency condition here that I can't write down. The contingent ingredients, the ingredients that will vary from one run of the system to another, are initial conditions, and in particular, whatever the standalone probability distribution is. In particular, if you're given the standalone probability distribution at one of the conditioning times, then the laws will tell you by the law of total probability what the standalone probabilities will be at any other target time. Again, the target times are from the continuum. There is no fundamental discreteness of time involved here. The fact that this is a linear rule, linear given the laws, linear between the initial and final standalone probabilities, will be important later. And now what I have to do is establish a correspondence between theories like this and quantum theories. I will first argue that every one of these theories has a Hilbert space description. Here's how it works. This is a bit technical. On my construction, and I should say there are now some papers in the archive where people have found slightly more elegant constructions, which I'm very happy about. This is my original construction. We take the dynamical laws for, let's say, one of those initial, one of those conditioning times, which I've just chosen to be 0 without loss of generality. It's non-negative. All the entries of this matrix of conditional probabilities are all non-negative. So by definition, we can always express them as the modulus squared of another matrix, of the entries of another matrix. That's the theta matrix, which could be complex valued. This new matrix satisfies the following sum rule, which just follows from the fact that the conditional probabilities are a probability distribution. If you sum down a column, you have to get 1 because it's the probability distribution. We introduce take the initial probabilities, the standalone probabilities at that time 0, we put them into a diagonal matrix, and then we sandwich them between theta and theta dagger. That defines a time-dependent density matrix. If gamma is unistochastic, which is a term introduced with the modern terminology in 1989 in a Johns Hopkins lecture by Thompson that I cannot find. If anyone can find it, please tell me. But the concept was introduced in 1954. It was under a different name, orthostochastic, by Alfred Horn. A matrix is unistochastic just in the case that theta can be taken to be unitary. A matrix, a square matrix whose entries are the mod squares of the entries of a same size, same shape unitary matrix, is called unistochastic. If gamma is unistochastic, then by definition, there exists a U that we can use instead of theta where U is unitary. Crucially, if it's not unistochastic, if it's some generic stochastic matrix, not a problem. Because you can prove, I proved, that theta can be expressed as a quantum channel, completely positive trace preserving that, and then by Sine-Spring's dilation theorem, also a 1950s theorem, you can dilate it into a unitary map anyway. And so there exists a Hilbert space, maybe with dimension bigger than n, but bounded in dimension, for which you can still represent this system using unitary evolution anyway. So you get an emergent quantum system in a Hilbert space representation with unitary evolution, and the fact that the underlying law of total probability introduced before is linear is what underwrites the linearity of time evolution for that density matrix. And this is a first principles explanation for why we use unitary evolution in quantum mechanics, and in particular, why that evolution is linear. Those are mysteries otherwise, postulates. Here we can understand where they could be coming from. Now I'm going to come back to that interference question. I claimed that interference was nothing other than a discrepancy between non-Markovian evolution and Markov evolution. Let's see that explicitly. So now that we have a unitary matrix for evolution, maybe on a bigger Hilbert space, I can take that unitary matrix from my conditioning time 0 to a time t, a target time t, a different target time t prime. I can multiply them together like this, daggering one of them, multiplying by the other, that's on the right, and use this to define this purple unitary that now I'm labeling as goes from t prime to t. If I rearrange this definition, I get a composition law. Wait a second. This looks like a division rule. I thought we said that this system was not divisible. What's going on here? Well, I said the punchline. The punchline was that the purpose of the Hilbert space representation was to allow us a representation in which we have a semblance of divisibility. The underlying process is still indivisible. And if what you try to do is define that purple matrix that's missing anyway, by taking the purple U matrix, which we do have, mod squaring its individual entries, and using it to define a stochastic matrix, and then seeing, well, can I use this purple matrix anyway? You'll get the wrong answer. There will be discrepancy between the correct evolution, that's the Brown law all the way on the left. Sorry, Brown University, sorry, Brown on the left. And then the Markov approximation next to it. And that difference you can calculate is exactly the formula for quantum mechanical interference, like literally exactly. So again, this suggests that interference in quantum mechanics is not some exotic phenomenon, but just a particular instance of a more general breakdown of Markov assumptions. Every time you predict something using a Markov assumption, it is not quite right. The discrepancies are just interference. And quantum mechanical interference is only one special kind of this. What of the wave function? Well, if the density matrix happens to be rank 1, we can factorize it. Talked about that before. And then the state vector with which we factorize it, you can show satisfies this equation if the unitary is strongly continuous. And the linearity of the Schrodinger equation descends from the linearity of that marginalization rule for the stochastic laws from before. And so we see that wave functions and the Schrodinger equation are secondary pieces of derived mathematics, not primary ontological furniture. Wave functions are, from this view, not purely epistemic. Epistemic means about knowledge and belief, about our uncertainty, our personal uncertainty. They are representational things. They represent a blend of epistemic and law-like nomological information. They're not physical or ontological objects from this point of view. They're like the ether or Magritte's famous pipe. Okay. And then the standard unitary Hilbert space formalism formally yields a divisible first-order differential equation for the dynamics. Basically, you get what's called a hidden Markov model in language introduced in the 80s. Okay, now we can also go backward. If you give me a unitary evolving quantum system, I just mod square the entries, and that defines the stochastic matrix. And you can just recreate all the results of quantum mechanics this way. Now, a question people often ask is, if I mod square all the entries of U to get a stochastic matrix, am I not losing phase information? And the answer is you are, if you're trying to study a quantum system with an external observer not included in the formalism. And you can do that if you want to just do standard orthodox Dirac-von quantum mechanics. But if you model the measuring device and the external observer and the environment all as more quantum systems, as just one big system evolving stochastically, then the phase information is irrelevant. Because the probabilities for the external observer and the measuring device to land at their measured results come out in line with the Born rule. The phases are irrelevant. The phases are only needed if you would like to exclude the observer, simplify your formalism, and basically resurrect the measurement problem. Okay, now we can go both ways. This means we have a correspondence. We arrive at a stochastic quantum correspondence. The correspondence is many to one in both directions. And it's kind of like the relationship between Newtonian mechanics and the Hamiltonian formulation. Hamiltonian phase space mechanics, there's many to one in both directions. Like any form of analytical mechanics, whether it's classical Hamiltonian mechanics or the Hilbert space formalism, that analytical mechanics provides us with very precise surgical tools for constructing theories, studying symmetries, and so forth. I call this underlying picture of quantum theory the indivisible formulation or indivisible quantum theory. Okay. Now, the last part of the talk, Bell's theorem and Tsirelson bound. I have a question for all of you. The conventional wisdom you may hear about hidden variables and causal locality in quantum theory are what? What does Bell's theorem tell us? What does Bell's theorem tell us? How many of you have heard of Bell's theorem? How many of you have read Bell's paper? Okay. What does Bell's theorem tell us? What have you been told? Okay, what have you been told by others Bell's theorem tells us?
I've been told by others that Bell's theorem discounts the possibility of a hidden variable theory to explain quantum.
Excellent. And by the way, that is what it says in the Nobel Prize announcement in 2022 for Aspe, Zeilinger, and John Clauser. Okay? That's what it says. That is, it says this. I've predicted the future. I've predicted what you're going to say. Now, some people will say, okay, if you push me, it doesn't rule them out, but it does say that there's a cost. If you have a hidden variables theory, it's got to be non-local, causally non-local. But as long as we don't have hidden variables, then we can keep locality or causal locality. Another thing you hear from some people is that, no, what Bell's theorem establishes is quantum theory is just non-local or causally non-local. The hidden variables are immaterial. Right? Now, all these mutually compatible statements are widely disputed. It's worth noting that according to Bell himself, he was proving the third thing. Bell wasn't against hidden variables. He was trying to prove the third thing. And I'll explain in detail what's going on. And I'm going to argue that there's in fact a salvageable notion of causal locality, at least on a picture of quantum mechanics, which one I presented. We got to go back to the EPR paper, which I think we've established people didn't read the EPR paper. No, sorry. Here's the EPR paper. Einstein, Podolsky, and Rosen. They introduced an early version of quantum steering. The thought experiment is very simple. Alice and Bob, they receive a pair of particles produced at some local event. They both receive, each one receives a particle. They're very far apart. They actually don't say far apart in the paper, but the authors assume that they are somehow not in interaction or communication. Each one receives a particle. Alice measures her particle, and she can pick a basis to measure it, and she can pick which observable to measure. In the original APR paper, it was position or momentum. In later work, Bohm's formulation in particular, it was a choice of spin axis. But Alice can pick what observable she wants to measure, and then her choice of measurement observable collapses the overall entangled quantum state in such a way that Bob's particle collapses to the same basis. So Alice can steer, from this point of view, Bob's collapse basis. She can pick whatever observable she wants to measure, and by collapsing her particle to that basis, she can make Bob's particle collapse to the same basis. This Schrödinger called quantum steering, which is very confusing. Now, Alice cannot pick the answer she gets from her measurement. She can't make her answer be spin up every time. And because she can't do that, she can't control what answer Bob gets. Bob's answer will be correlated in some way. Her answers are random, so Bob's answers will be random, and they'll be correlated. But because she can't control what result she gets, she can't use this to signal. She can't send messages. Okay. So Alice can seemingly steer Bob's particle to a chosen collapse basis in language due to Schrödinger. However, the no signaling theorem prohibits Alice from controlling the specific wave function of Bob's particle in the collapse basis. And what EPR believed they had done was set up a logical fork. Okay. So either non-local steering is causally changing something over at Bob.
I non-locally steer that.
Thank you, Kelly. Or Bob's particle already knew all the outcomes it was going to have anyway. And if that's the case, then those outcomes, which Bob's particle already knew, being as they are not represented in the overall wave function, are information above and beyond the wave function, and therefore quantum mechanics is incomplete. Podolsky-Rosen took for granted that there couldn't actually be any causal action at a distance, so they regarded this as a proof that quantum mechanics had to be incomplete. Okay. Bell argued in his paper that the second prong of the fork did not actually let you escape causal non-locality. That's what Bell thought he was doing. He thought he was closing this logical fork. If you thought you could have either non-local steering or hidden variables, Bell argued that hidden variables could not save you from the non-locality. Not that hidden variables were responsible for non-locality, which is how this paper has been misunderstood because no one reads it, as we've just established. Just a game of telephone. Here is Bell's inequality in one slide. Alice can locally measure either property A or A prime of her particle, and we'll assume for simplicity each of them has only two possible values, plus or minus one. Bob, similarly, he can measure one of two properties, B or B prime, each of which is bivalent, has values plus or minus one. I will define a new variable C to be this particular combination. If you look at this, you'll go, wait a second. So on a given run, if it is the case that B and B prime have the same value, then the first term is going to be plus or minus 2, and the second term is going to be 0. If it's the case that B and B prime have different values, opposite values, then the first term will be 0, and the second term will be plus or minus 2. And therefore, this quantity C is guaranteed to have a value plus or minus 2 in any run of the experiment, and therefore its average will have to be somewhere between plus or minus 2. And you also do this by some trivial arithmetic. Just square C and simplify, and you'll find that C is always plus or minus 2, and that means the average value of C. If I have a random thing that can sometimes be 2 and sometimes minus 2, the average will have to be somewhere in between. And if we just take that alternative formula for C and plug it in, we get the Bell CHS inequality. This is a miniature derivation of the Bell CHS inequality. You shouldn't be able to get a value bigger than 2. Now, quantum theory, it turns out, can slightly violate this, but only by a factor of root 2. Now, what's root 2? 1.414. So this is like a 41% violation. Why only that much? Maybe because any more than that could let signaling happen, which we know is bad. Turns out that's not true. So Tsirelson showed this was the maximal violation you get from quantum mechanics. In fact, you get it with maximally entangled particles. I'll show in a minute that you can, in fact, get bigger values if you only impose no signaling. Anyway, so how do we do this in practice? Well, like I said, we measure this empirically by conducting the experiment many times. N times where n is large, we measure C each time, and then we add them up and we divide. But of course, you can't measure C on every run of the experiment, because every run of the experiment, right, Alice has to pick A or B, or A or A prime, and Bob has to pick B or B prime. So really, this experiment is done this way. In some of the runs, randomly Alice measures A and Bob measures B. In other runs, Alice measures A and Bob measures B prime. In other runs, Alice measures A prime and Bob measures B. And in finally other runs, they measure A prime and B prime. Notice I have approximated the first average with this second average. What justified that? It's not clear what justifies that move. That move is suspect. In that move, I have replaced my unconditioned average with averages conditioned on the choices of measurements done by Alice and Bob. 4 different averages, each conditioned on what measurement in fact was done. Okay? This is a suspicious but crucial move. It amounts to conditioning in each term. Now, if these particles could truly communicate non-locally, if they're really whispering to each other, I'm Alice's particle. Alice measured A and got +1. Bob, if Bob's particle, Bob measures B, you do +1. If Bob measures B prime, also do +1. Right? If the particles can communicate to each other like that, they can ensure that every term in this is always +1, +1, +1, and -1, which is +1. And they can ensure that every run the answer is 4. And so if the particles can communicate secretly, they should be able to get a value of 4. And what Popescu and Rohrlich showed is that this is compatible with no signaling. The particles can secretly talk to each other without letting Alice and Bob know about it or send messages. And if all you're imposing is signaling is not allowed, you should be able to get a value as big as 4. And yet we don't. We only get 2√2. And Popescu and Rohrlich were hoping that no signaling alone could tell you why you get this mysterious 2√2, and that failed. No signaling, the prohibition of Alice and Bob sending messages to each other, lets you go up to 100% violations of Bell. Why such a small violation? Why the Tsirelson ban? And to explain this, we need to talk about causation. This is the last part of the talk. Quantum mechanics definitely features non-local correlation, but there are non-local correlations all over the place. We see non-local correlations all over the place. Why should we be particularly concerned about quantum mechanics, especially because the non-local correlations do not involve signaling? By contrast, naive Newtonian gravity, instantaneous gravitational action at a distance, should allow signaling. I can wobble a mass here, and if naive Newtonian gravity is true, people can detect it anywhere, and I can send messages this way. Quantum mechanics doesn't let you do that. So it's not obvious why we should be worried about non-locality if it's not signaling. Is there some kind of unacceptable non-locality in between just mere correlation, which we're not worried about, and signaling that we should be worried about? What really would make us worry is if it's causal, but then there's no avoiding talking about what causation means. Now, everyone knows that correlation does not imply causation, but then how do we move from questions of mere non-local correlation in quantum theory to statements about non-local causation? And this is where all of the problems show up. I should say, and I promised I would quote Everett from his long form thesis. This is what he said. This is the final paragraph of his thesis. This is what he says. As a final note, we might comment upon the concept of causality. It should be clearly recognized that causality is a property of a model and not a property of the world of experience. The concept of causality only makes sense with reference to a theory in which there are logical dependencies among the elements. A theory contains relations of the form A implies B, which can be read as A causes B, while our experience, uninterpreted by any theory, gives nothing of the sort, but only a correlation between the event corresponding to B and that corresponding to A. I agree with this. If you're walking around the world and just seeing correlations without some kind of physical theory that sets up some kind of connections between things, I am very suspicious that what you're looking at is some kind of fundamental notion of causation. Now, of course, in causal discovery, if you're doing drug development, medicine, or social sciences, whatever, we use all kinds of correlations to suss out, to discover causal relationships. But the question is, what are those causal relationships? What do they consist of? If you believe there truly is a causal relationship, you have to talk about causation. And at least if we're talking about a fundamental microscopic theory like quantum mechanics, I'm going to argue we need a constructive, definite statement of what it means to have causal relationships between things. The first step toward this is to note a key connection with another theory, the theory of Bayesian networks. Theory of Bayesian networks, one considers a set of random variables, as we talked about, related by a collection of basic directed conditional probabilities. So here's a graphical depiction of such a thing. These are all random variables and with arrows between them. We have a simple Bayesian network with 4 random variables, A, B, C, and D. I'm using some color coding here that supplies a basic directed conditional probability distribution. These arrows tell me that what this theory supplies in its basic rules or laws, its nomology, is a set of conditional probabilities of that form. Conditioned on B, C, and D, there is some probability distribution for A. And this means that I can call A the endogenous variable here, and B, C, and D the exogenous from the Latin for internal, external. And the idea is that B, C, and D are just doing their stuff, fluctuating whatever they're doing. And what they're doing is somehow influencing A, determining the probability distribution for A through this law. And I'm going to read that as a causal relationship, a basic causal relationship built out of law-like, lawful, nomological conditional probabilities connecting variables. Okay, so in a concrete instantiation of this Bayesian network, one has some contingent joint probability distribution for the exogenous variables. This induces a contingent standalone probability distribution for A according to the law of total probability. It's multilinear. One can define other conditional probability distributions. I mean, you can, for example, use the Bayes' theorem to invert this. You might go, well, if I can always invert this, why is there a privileged status for saying that the arrows go one way, not the other? Because notice from the color coding, this is why I'm using color coding, that to invert this, we have to introduce this very complicated non-linear formula that mixes together contingent information, the standalone probabilities of B, C, and D, which are contingent, with lawful information. And what we get, yes, is a well-defined conditional probability, but one that is run-dependent, contingent, not one that's lawful. So therefore not expressing a lawful form of conditional dependence, not a lawful form of causation. Now, I've been circulating in the field of causation, metaphysics of causation long enough to say this is not widely appreciated, but it's very important. And also has an interesting interplay with an old paper by Humphreys about propensity interpretations of causation, which we can have at Q&A. So the basic directed conditional probabilities, the Brown ones, supplied by the Bayesian network, have a more fundamental status as the laws of the model. And we're going to make the move and regard them as defining a notion of taking this seriously. We can argue that supplying those conditional probabilities in the laws, we're asserting a causal influence from B, C, and D to A. And that's what I'm going to take to be my definition of the causal influence from the laws. Notice that they are directed, which neatly captures the asymmetric relationship between causes and effects. Yet it does so without, I didn't say the word time anywhere. You could imagine a universe that was set up in the opposite time direction in which all the relationships are reversed. That's totally fine. There's no privileging of future to past. This threads a very thin needle in giving you an asymmetry between causes and effects without fundamentally specifying a fundamental arrow of time of the universe. So we arrive at a nomological theory of causation grounded in the indivisible theory I presented, whose laws are in fact conditional probabilities of the kind we just talked about. And so we can read on this argument, we can read those conditional laws as causal laws, laws that are causal, that specify causal relationships. And therefore the indivisible theory provides a hospitable domain for causal talk. Okay? So one can argue, apply a causal reading to these nomological conditional probabilities, motivating a new theory of causation. Here it is. This is my nomological theory of causation on a theory X to say that the variables B, C, and so forth have nomological causal influences on a variable A is just to say that the theory X specifies in its basic fixed laws a conditional probability of the form P of A given B, C, and so forth, read as a nomological conditional probability of A given B, C, and so forth. This is my theory. In that sense, one can regard the indivisible theory as a nomological theory of causation par excellence. And now we can talk about causal independence. I will say that Q is free of causal influences from R over the time interval from 0 to T in question, if after marginalizing over R, Q has its own conditional probability distribution that doesn't depend on R at all. This is what I take causal independence to mean. This includes, as a special case, that the conditional probabilities factorize are statistically independent. That will also ensure this. But more generally, when Q has its own causal laws, conditional probabilities that don't depend on R, that's when we say that Q is causally independent of R. That is going to be my definition of what it means for things to be out of causal contact. Now I have rigorous constructive definitions of these things rather than relying on a principles theoretical derivation of causation starting from abstract principles. And now we can specify my principle of causal locality, which I'm arguing is better than Bell's principle. A theory with microphysical directed conditional probabilities, like the indivisible theory, is causally local if any pair of localized systems, Q and R, that remain at space-like separation in a given situation, never exert causal influences on each other in the sense that the directed conditional probabilities for Q are independent of R and vice versa. This is a precise, constructive definition of what it means to be causally local. It is then a straightforward calculation to show this principle is satisfied by the indivisible theory. Here's the calculation. It's an annoying calculation that you could just do, and there it is. You want to see it, kind of go through the calculation in front of all of you, but there it is. It's in the papers. You can see it all works. You get the appropriate behavior for systems that are space-like separated. Okay. By contrast, if Q and R are not kept at space-like separation and they are allowed to interact at some interaction time t, this breaks down. At some point, we lose this factorization of the unitaries, and we get a violation of the factorization of the conditional probabilities at all later times. So if there's ever an interaction between them, the laws for the two systems do not factorize between the two systems at later times, and this is exactly what entanglement is. So this is a completely non-quantum, non-Hilbert space definition of what it means to have entanglement. The laws of the two systems do not factorize into separate laws. Okay? So this is now entanglement is manifest level of the underlying indivisible stochastic process. The two systems are exerting causal influence on each other because they had a local interaction at some time in the past. There's nothing causally non-local about this at all. Now we can go back to the EPR experiment. If we add observer subsystems A and B explicitly to the EPR experiment and just run the experiment again, the two particles are together at time 0. They're allowed to interact up until some time t prime. Then they separate. This is a space-time diagram. Particle Q goes to Alice A. Particle R goes to Bob B. You can just compute the conditional probabilities for Alice and show explicitly that all the dependence on Bob goes away. There's no causal influence from Bob's experiment to Alice or vice versa. You could also show that if you enlarge this and take Alice and her particle together, they are also causally independent of Bob. And there's just no non-local causation in this structure. The only causal influences on A come from Q and R, but they're both in the past light cone. So all this works out just nicely. And now the final slide, the Tsirelson bound. We can rephrase the Bell CHS equality as a game of, I keep wanting to say Game of Thrones. It's not a Game of Thrones. It's a game of bits. Very small thrones that can either be occupied or unoccupied. Alice, Bob, and now Charlie are allowed to plan a strategy ahead of time. They can plan, and then they're going to begin a game. Here's the game works. Alice is going to randomize a bit X, and then, maybe conditioned on that X, choose a bit Q. Each of them is a bit, 0 or 1, and sends them to Charlie. Bob does exactly the same thing. He randomizes a bit Y, and then chooses a bit R that can depend on Y, sends them to Charlie. We can think in here of X and Y, the randomized bit as a randomized choice of setting, and Q and R as maybe dependent on the choice of setting, the outcome bits. Charlie then tests the following equality. That's addition modulo 2. Addition mod 2, Q plus R mod 2. Charlie's just going to check whether Q plus R mod 2 gives the same answer as X times Y, and assigns +1 points for yes and -1 for no. We can calculate the average score by taking the probability distribution over X, Y, Q, and R, assigning +1 point, that's the Kronecker delta over there, when that equality it holds. That's +1 point, -1 point when they don't hold, and then we're just averaging over the possibilities, and that gives the average score. You can easily check that this average score is just the Bell variable C divided by 4. Easy to check that's true. If Alice and Bob generate X and Y uniformly, randomly, with probabilities each quarter, then the score is given by this formula. And the Bell CHS inequality, remember, C is bounded by 2, gives the following inequality for the score. 4 times the score must be less than or equal to 2. I almost said 4 score. If you allow PR boxes, you can Popescu-Roerlich boxes, you can get up to 4. What we showed in our paper, and this is me and my colleague David, what we showed is that if you just take that causal locality requirement that we imposed, no causal influences of space-like separation, the theory is causally local, you hit 2 root 2 on the nose. And as far as we know, this is the first principles derivation of the Tsirelson inequality. That doesn't just say, well, you have to assume all of quantum mechanics and assume that your measurement operators have certain factorization properties and assume all this sort of technical stuff. This is the conceptual explanation for why that is. And this is our chief result. There's the Tsirelson bound. So to conclude, this approach gives new ways to think about our generalized dynamical symmetries, implications for all problem system mechanics, yada, 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 lots of stuff, okay? I'm particularly interested in building self-consistent generalizations of quantum theory and potential applications for quantum gravity, and maybe some interesting engineering applications. Very interesting stuff. And that's the end of my talk. Thank you. Okay, I'm happy to take questions. All questions, no questions too big or too small, too existential, and not. Yes, what's your name?
Right.
Ray, nice to meet you.
Two metaphysics-y wouldn't be a problem.
There is no such thing as two metaphysics-y.
Awesome, okay. So you stated that wave functions aren't really epistemic and that they also have this gnomic quality. But at the beginning of the talk, I started putting into Tsirelson's view that we should treat wave functions as like purely representational, that we shouldn't ask like what they are ontologically speaking, but instead what they represent. So if my interpretation of that is correct, I was wondering if you would mind clarifying how you're thinking about the wave function in its gnomic role. Like what is it to be a law?
It's a lovely question. If I may, I'm going to situate that question a little bit. Hans Halvorsen is a philosopher of physics, Princeton. His specialty is algebraic quantum field theory. So he spends a lot of time thinking about C-star algebraic formulations of quantum theory. And on those views, things like wave functions are ingredients of Hilbert space representations. And so they're very representation dependent. So the question is, how am I thinking about the wave function here? I'm thinking about the wave function as a piece of mathematics. I'm thinking about the wave function as just a calculational device or a tool. The closest, the most conceptually similar kind of mathematical appurtenance I have in mind is a Hamilton-Jacobi function, which after all is where the wave function came from. So those of you who aren't familiar with Hamilton-Jacobi formulation, how many of you know what the principle of least action is? You heard the principle is that just Lagrangian kinetic minus potential energy for simple systems integrated over time, and we optimize this, and this tells us the path the system takes. It turns out that if you solve the system's equations of motion and integrate to get the actual action, but regard the final endpoint and end time as variable, this is called the Hamilton-Jacobi function. It satisfies a partial differential equation, and this partial differential equation looks a lot like the Schrodinger equation, and Schrodinger identified it as the high frequency or iconal approximation of a wave equation, and that is how he arrived at the Schrodinger equation. In Schrodinger's original formulation, the wave function was just an exponentiation of the Hamilton-Jacobi function. And so arguably they serve the same role. I don't think that the Hamilton-Jacobi function is a physical object. It lives in configuration space, just like the wave function does. It's very useful for some calculations, although not most calculations an undergraduate is likely to see, but some more advanced calculations. So for some calculations, it's an incredibly useful tool. It's great for visualization, but I don't think it's a fundamental object. It encodes some kind of information about initial conditions and the laws of the theory.
So it's
Yeah.
the sort of thing that does something rather than the best description of what there is.
That's right. I don't think it's a description of what there is. I think it's a useful mathematical tool.
Yeah. The pragmatic view.
I would say that I have a pragmatic view toward the wave function, yes. I think that would be a fair characterization. I would say my view better is a deflationary view, a metaphysically deflationary view. The wave function is not something that needs to be explained in some strong way, that once you understand what the wave function is and what it's doing, you no longer feel a need to explain what it is. It's just another piece of the mathematics. More questions? Yes, what's your name?
Kong-san,
Nice to meet you.
nice to meet you too. What then is the deal with something like an underlying probability distribution? Is this also just like a description of some phenomena, or is it just like, is this something maybe inherent to like the phenomenon you're describing, or is it just like something useful to model it? Or
So,
is this, yeah.
This is a great, and I cut some slides on exactly that question because as you can tell, I ran over time. So I'm glad you brought this up in the Q&A. The metaphysics of probability is so rich and interesting, and I touched on it a little bit when I said, oh, there's no like rigorous way to understand why we can experimentally obtain expectation values by just repeating trials many times. Like that's a giant mystery. Why is it a mystery? I made some references to why the law of large numbers doesn't give you a non-circular definition of why this is. I'm teaching a class next year on the philosophy of probability. So this is all very close to my heart. The best I can say is that I think that chancy, objective chancy type dynamical dice rolling type probabilities, they don't have to be, okay. So we often associate dynamical probabilities with things that change with time. These are called diachronic probabilities. Synchronic probabilities would be just like laws that specify there are just probabilities at one time. Like there's some distribution of probability distribution over the initial conditions of the universe would be synchronic. I think it's fine for a theory to have objective probabilities as a part of the laws. And so I would ground at least some of the probabilities here in the laws of the theory and say that they are nomological. This is not all the probabilities in the theory, because there's also the standalone probabilities that are related to each other by the nomological conditional probabilities. And those standalone, so the dynamical probabilities are diachronic. They connect 2 times, they proceed over time. The standalone probabilities are synchronic. Are they best understood as some kind of law-like thing? I think they can't just be a law because they're contingent. After all, like, they vary from one run to the other. They're the contingent things. So they're at least not fully law-like. When you propagate them forward using the laws, even if the initial probabilities were epistemic, meaning just up to us, credences, our beliefs, our uncertainty, once you propagate them forward with the laws, the later ones are going to now be a mixture of both your initial epistemic uncertainty, and now they're mixed because they're infused with the dynamical probabilities that were parts of your laws. So the best I can say is I take the dynamical conditional probabilities to be grounded in laws, and I take all the other probabilities that come out to be some possible mixture of maybe some epistemic and definitely some nomological stuff. Now, to say that I've grounded my probabilities in laws then just shifts the question of what do I mean by laws, and what is the physical theory and what are the laws of the theory. And there's a whole other area of metaphysics, the metaphysics of laws of nature, that I just cannot possibly describe in this talk. Maybe the laws are fundamental, they're primitive features of reality. Maybe they are themselves reducible to or grounded in something non-law-like. That's the so-called Humean view, broadly construed. So the answer is, there's just so many things to say here. I can't possibly do justice here. So you ask me a question, and rather than answer it, I'm just saying your question actually plugs into a vein of just enormous abundance that I cannot possibly do justice to. And for that, I apologize deeply.
You accept it?
Thank you. That's so nice of you. Yes, what's your name?
I was wondering, what kind of factors do you think drive academics away from working on this stuff and sort of explains kind of this sociological history?
What drives academics away from this and explains the sociological history? That is a fantastic question. We have a couple of philosophers of physics in the audience. Does anyone want to offer up some ideas? I'm so curious to hear from others. I'm not an expert on sociology or history. Anyone have any thoughts? Anyone willing to contribute to this? Genuine curiosity, because I'd love to hear from people.
I don't think you have to be a philosopher to answer the question either.
I'd love to hear from people who are more maybe senior, established in physics, or been around physics. Do you have any idea? What are you hearing from people? What do people say? What do you hear from people? David, you can't answer. No, David, you can't. You're a ringer. You can't answer. Someone else. David and I, we both know.
Yeah.
We've been talking about this for how many years now? Right.
I mean, during my time as a master's student in physics, I was explicitly discouraged from pursuing any sort of foundational or philosophical questions in physics.
You were just explicitly discouraged, and what did they tell you? Why did they discourage you?
This is the way to get into a physics PhD program. There's no money in it.
There's no money in it, there's no funding, there's no jobs, it's not serious. All those things I said in the first slide. So I wasn't just blowing smoke. That's all stuff we hear. I won't, okay. But why? The question I think that was asked is, why is it like that? Why do you think it's like that? Anyone have any ideas? I'm genuinely curious. I'm not sitting here being like, I know the answer.
Is it like a Cold War sentiment of calculating, being a computer? Physicists should be a computer.
Physicists should be computer. We should shut up and calculate, as David Merman put it in a 1989 article in Physics Today. What's wrong with this pillow, I think, right?
Maybe computers in the 20s, that's kind of fun.
That's right, yeah. Ray, what do you think?
I mean, during World War II, so many physicists were pulled into the atomic bomb or whatever. So suddenly physics had this utility that maybe it didn't have before. And I think at this stage we were asked to take on more practical problems than what's the ontology of wave function and what have you. But prior to that, I think these questions were entertained frequently. Like Einstein's obviously a philosopher, and all these guys who were writing letters to each other in the 1920s and 30s were touching on really deep philosophical problems.
Yeah. So yeah, and this is an explanation that I agree with. Yeah, I think it's that it's a matter of historical contingency, the shift of physics after World War II to America, a much more pragmatic place. big money used for building important things for practical purposes. And there's a lot to do. We don't have time to worry about these things. But then how do we account for all the work that went on in quantum gravity? All the work that went on in cosmology, all the work that by the 1950s and 60s and beyond were going into string theory, arguably very far away from practical use. People often told me that the measurement problem is not worth studying because it's too hard to do experiments. It's too removed. That vigorous fun thought experiment to do it in practice, right, it would require a control of thermodynamically numerously many degrees of freedom that would be akin to having the control of like unscrambling an egg or raising the dead. And I say raising the dead because there's a paper that introduces a theorem called the quantum necromancy theorem that shows that if you could experimentally test the difference between the different branches of that flowchart in the vigorous fun experiment, then you could also bring a cat back to life from the dead. Okay? So highly impractical. But you know what's even more impractical? The black hole information problem. Sorry to bring that up. Right? Black hole information problem is about a gazillion times harder to do experimentally in the vigorous fun thought experiment. And many departments have spent enormous amounts of effort on that problem. People who will talk about that and then turn around and say, yeah, but measurement problem is too hard to do, too irrelevant.
I just want to add
David.
a little nuance, which is that quantum gravity was also a career killer, I think, up until the 80s, right? Like, it was a very narrow group. I mean, you had like some people kind of off on the side calculating, showing non-normal, whatever, but the young people weren't supposed to, right? And then
That's a fair point.
and then like I think string theory kind of flew it up, like then caught on. And so there's a little
That's a fair point. Fair point.
I think like maybe it's something that physics got to a point where it requires such mathematical rigor that although a lot of people are interested in philosophical questions, by the time they go through all that mathematics training, it's only a minority that made it through that still are interested in philosophical questions to begin with. So then it just becomes stigmatized, and the majority of them are more interested in just kind of simple manipulation or mathematics, just as a selection bias, if that makes sense.
That's also a great idea. I like that suggestion as well. These are great. Yeah, please, go ahead.
I'm saying this like PhD student, you get to a point where you're done taking classes, but you realize like how minimal your physics education is, right? Like very, very, very minimal. Especially if you're doing things that aren't theoretical. And so the idea that somewhere in there, you're also going to be learning things that require more understanding than you ever actually build is quite difficult. Like, there's just so much to get to that point. It's difficult to fit in.
That's great. Yes.
I think technology and not just like but just like evolution of information in general, it's become so heavily reliant on empirics. Kind of like what Sean was saying, and like an entire element. I think the spark of the human mind that initiates the study of those empirics starts to become undervalued. And we forget that any new information begins with that spark.
I guess so. I like these are all great. I guess what I'm trying to understand is what was special about quantum foundations in particular, because a lot of these concerns, which I think certainly do apply to quantum foundations, could have applied to lots of other areas of science, but didn't. Or they did for some amount of time, and then for reasons that are complicated, they
It
changed.
might be interesting to understand why the divergence.
Right.
And again, I think string theory is a big part of that story. With quantum gravity becoming kosher, so to speak.
Sure, but Richard Feynman, he delivered his lectures on quantum gravity pretty early on, right? This was well before the 80s. Say what?
That he was fine, right? Like,
But that's the point. Why did Feynman, who was very prestigious, decide that was a good use of his time?
yeah.
And Weinberg was doing some very important fundamental work on quantum gravity in the 60s.
Sure.
Like, there were very, very serious, prominent, prestigious people who did think about and work on these problems and publish in journals in good stead at a time. So this is interesting. Weinberg published my favorite of those papers in 1964.
Right.
And maybe you know this, but 1964 was the same year Bell's theorem was published, also the year that the quark model was proposed, and the year that Penzias and Wilson discovered the cosmic microwave background radiation. That was all 64. And the year that Cronin and Fitch discovered experimentally CP violation, therefore time reversal violation in nature. And also, exactly 400 years after the birth of Galileo, 1564, which was also the same year that Shakespeare and Marlowe were born. 1564. That kind of correlation cries out for explanation.
Building off of somebody's answer question, so you mentioned that the victims of friend thought experiment would be very experimentally difficult. But I think, I mean, I know, and it's only recently that we've been able to, but there are groups that are now looking to test theories of quantum gravity by creating like bigger and bigger macroscopic superpositions. So are there similar recent developments in smaller scale experiments that could somehow empirically provide evidence that might at some point empirically distinguish interpretation of quantum mechanics in the same way that maybe we're getting to a point where we could empirically distinguish theories of quantum gravity?
That's a great question. So over here, the question was, we have made some progress in experiments that do appear to be probing at least maybe some aspects of quantum gravity in a limited way. What is the prospect for experiments, maybe early experiments, early development experiments that might be able to help us distinguish between interpretations of quantum mechanics, like in that flowchart? There are not a lot. There are many experiments involving what are called weak measurements and weak values that claim to be probing these foundational questions, and I think they're all wrong, fundamentally wrong, and I have papers on why that doesn't work, why they all entail assuming the thing to be found in the experiments and are not good experiments. So you occasionally hear reports of, oh, we've seen the trajectories in Bohmian mechanics. We visualize them using weak values and weak measurements, and I think that doesn't work.
This is the Tetra cat.
Quantum Tetra Cat's an example of this as well. I think they're all fundamentally mistaken. So I think a lot of those experiments, unfortunately, don't tell us anything. And for the other reason that they would give exactly the same results regardless of interpretation.
Yeah.
So they can't possibly be telling us about what's really going on. There are some interesting, now I'm just sort of like, speculating a little bit, but there was an interesting experiment proposed by Jennifer Glick and Christoph Adami in a paper from 2019, 2020. And interestingly, it was like Markovian and non-Markovian quantum measurements. I think that's what the paper was called, something like that title. And they proposed a very ingenious generalization of the Wigner's friend thought experiment. They didn't mention Wigner's friend in the paper. I don't quite know why. But what they set up was basically an iterated version of the Wigner's friend thought experiment, where instead of one friend in the box, I mean, who wants just one friend?
Yeah.
Especially if you're stuck in a box.
Especially if you're stuck in a box, you want lots of friends. We all want lots of friends, don't we? Yeah, we all want lots of friends. So now instead of one friend, there are n friends in the box. N. And of course, there's Wigner still on the outside, but now there's n friends in the box. Still one quantum system, though. And the friends iteratively carry out a quantum measurement of that system. There's no reinitialization of the quantum system. It's not re-prepared in some prepared state. One friend conducts a quantum measurement on it, on some observable. Then the next friend comes and conducts a measurement on it, maybe some other observable, and so on and so on and so on and so on. And now you can ask, if Wigner at the end opens the box and wants to predict what will be found on opening the box, or will the predictions differ depending on whether Wigner assumed that each iterative step was a collapse or not? What was the whole sequence of those individual measurements all unitary process two evolution, or was each measurement a process one collapse evolution? And what they argued is that if you assume collapse at every individual measurement, then there is an even stronger kind of Markovianity that the system follows, stronger than even the Markovianity of just the divisibility of the time evolution operator. There's a real sense that on every measurement, any past information of previous measurements is just wiped out, like completely wiped clean. And so there's some sense in which at the end, all that Wigner really needs is somehow the final, the last measurement outcome. Whereas if we do not use process one evolution, no collapse, we just allow the whole thing to be unitary process two until the end, and then one final measurement is done, then the whole non-Markovian memory of the experiments is salient to the final prediction. Now, You can't do this with a macroscopic friend or macroscopic friends for all the reasons we said, but you could imagine doing it with a sequence of very, very small friends, microscopic friends. I'm sorry, this is getting kind of weird. Microscopic friends, but these are not imaginary friends, I promise. They're real. They're real. But maybe the idea is that if they're small enough, we can do these experiments and we can tell whether what was happening was collapse or not. Now, the problem, of course, is that if systems are very small, we have other reasons. For very small systems, everyone agrees aren't collapsing things. So you run into this question of if they're small enough that everybody would agree there's no collapse, then we're not really learning anything. And if they're big enough where there's really a question of whether they're collapsing, that may be too difficult to do experiment on. And so there's this question, can we realize this experiment? At the very least, this experiment does indicate there's a kind of non-Markovianity even in closed quantum systems. So if you look up non-Markovian in quantum, you'll find a zillion papers, but they're almost all about open quantum systems, where the non-Markovianity is fairly prosaic. When you have an open system classically or quantum mechanically, you can get feedback effects. The system acts on its environment, the environment can act back on the system, and these loops can give you non-Markovian effects where the past has some influence on the future through the environmental effects. This happens in classical physics and in quantum physics, and most papers on non-Markovianity quantum mechanics are about that kind of process. This is the Glickman-Adami non-Markovianity is the first example I've seen of someone writing down an explicit thought experiment that highlighted the presence of a kind of dynamical non-Markovianity for closed quantum systems. And it was under-recognized. I think it's actually a fantastic paper that people should read. So that would be a potential example, but I think it's still too hard to do the experiments in a way that would be revealing about which interpretation is correct. Yes, what's your name?
Tony, I like your interpretation of Rosetta. I have one comment is that the Dutch physicist Tooth, he commented on the quantum foundation as elephant in the room. People choose to escape on this spectrum, but he's studying quantum foundation. I think.
Yep. This is Gerhard Tuft. He's a Nobel Prize winning physicist. He won the Nobel Prize for proving the renormalizability of the standard model, which is kind of important. So he's been working on interpretations of quantum mechanics. He calls these the superdeterministic or the cellular automata interpretations of quantum mechanics. And to be perfectly honest, I don't think they're very promising. He puts a lot of metaphysical presuppositions on what he expects a theory to be. He'll still just say outright, I believe that a fundamental theory must be deterministic. And if you ask him why, he just says, that's my intuition. My intuition is that physical theories must be deterministic. And I just think that's a mistake. Like, it's not that we don't come into the world with any metaphysical premises or a priori hunches or inclinations or whatever. We do. You need some metaphysical premises just to get out of bed in the morning and get along in your day. To not believe that we're living in a radically skeptical hypothesis about the past. The universe did not, in fact, begin just 5 minutes ago with its full state intact. We do assume some things, like we think history happened or whatever. So lots of stuff we just took for granted. But I'm very nervous about taking on any more than we have to. So one thing I think is true is that there's something out there, some kind of ontology. After all, even the Dirac-Feynman axioms accept that external observers and measuring devices exist. If they didn't, there'd be nothing for there to be measurement outcomes on. And if once you accept those exist, you can then ask, well, why only those things? What's special about being a measuring device or an external observer? What else could there be? And can we have some theory of these ingredients that Bell called beables, the stuff that really exists? Not observables, but beables, like the things that can be. And then it's just a matter of what are your beables? How do you think they work together? And I'm trying to assume just that, basically, right? I'm trying to assume as little as possible. And then constraints on causal relationships from special relativity, which we have good empirically supported reasons to take seriously. For me to go along and say, and I insist the theory deterministic, that just seems like I'm asking for trouble because we have no reason to think nature should be so kind to us. Probabilistic theories are more general than deterministic theories. And I think that overlearning, overgeneralizing from past classical theories, whether about determinism or about Markovianity, Newton's theory is Markovian, approximately. If you think of velocities as being like instantaneous, you think there's Markov. I think overgeneralizing from the past success of those theories is in fact a mistake, and we should be very open-minded about what's out there. I am very open-minded. So I don't know if that answers your question.
Okay. And I do have another question. So
Sure.
in your formulation of the non-Markovian process, you factored the matrix gamma into a U matrix, right? But that introduces a very huge gauge group, right?
You better believe it. Yeah,
It's
it
a
certainly does.
huge gauge.
Huge gauge redundancy, exactly.
Right. And does this affect the final quantum mechanical results or observables?
Nope, precisely because they are gauge transformations. And in fact, Foldy Vautauge and gauge transformations are closely related to what you're describing. They mean that all of the mathematical regalia, the pertinences of the Hilbert space picture, unitary evolution operators, quantum state vectors, all of it, are all highly gauge dependent.
Yes.
However, you can prove that all of the empirical predictions of the theory, eigenvalue spectra, and Born probability distributions and Born grounded expectation values, all of those are invariant under those gauge transformations. And the question is, if those instrumentalist observational features of the theory are gauge invariant, is there some underlying ontological substrate out of which they're built that is gauge invariant? And the argument I made is it can't be Hilbert space ingredients precisely because they're so gauge dependent. And it doesn't bother me. I mean, my view is the whole Hilbert space picture is just representational, and so you can transform it in all kinds of ways, among those, these Foldy Vautauge and gauge transformations. I had a slide on these, but I removed it for time. As you can tell, we ran over time.
It is easier to prove when the gauge is just U1 or UN, but in your case, the gauge is more complicated, and I guess it's harder to prove that mathematically is stationary.
And not just Foldy Vautauge and gauge transformations. There's a whole other class of gauge transformations that came out of this work that have never been identified in the research literature to my knowledge. There are many, many ways in which the Hilbert space picture is highly non-unique.
Do we have a mathematical proof that even under those huge class of gauge transformations, the outcome is unchanged?
Yes.
Okay.
Yeah, it's easy to show.
Oh, okay.
Yeah.
I'm gonna ask a maybe more specific question about, you were introducing your phenomenological theory of causation. The example you gave, the graph, I mean, you go back to the graph, or the page and that. This one I called. You know, sorry, there's not much trouble.
It's not too much trouble.
Okay. So all the arrows, yeah, so it was A had multiple causes. But what if A was a common cause for B, C, and D? And so whenever A occurs, B occurs, C occurs, D occurs. So the probability of B given C, and if you didn't know about A, but you knew that every time A happens, both B and C happen, because these are the only things that cause B and C, then you would think that every time B happens, C also happens. And so I guess what I'm wondering is, what does common cause, which in this case is just kind of a mere correlation, look like in your picture?
So let me just quickly first say that the kind of causal influences I'm talking about here are what you might call generic causation, not single instance causation. This is related to the terminology of token versus type causation.
Okay.
I'm talking about statistical influences between things. I'm not saying here that C happens and then A happens as like single instance events, like someone throws a rock and then a window breaks. Did the throwing of the rock cause the window to break? That's a single instance kind of causation. This is more like you take certain medicines, and if you take certain medicines, does it change the probability you'll end up with a certain disease? That's not single instance causation. It's generic, or people differ on exactly the right terminology you want to use for it. That's the level of causation I'm talking about here. I'm saying that the values of B, C, and D, whatever values they have, are connected to the values of A through conditional probabilities. That is, A's probability distribution is dependent on the values of B, C, and D. That's what I mean when I say there's a causal influence. So it's a little more nuanced than, yeah. Now you can talk about common causes in causal diagrams like this. And there's a whole literature on how to situate common causes into causal modeling. And there's a whole bunch of desiderata that we place in causal models. And there's a whole theory here, and there's an interesting interplay. So this is, I keep mentioning this 1919 dichotomy that Einstein, so Einstein wrote an article in the Times of London, 1919, where he introduced this dichotomy between principal theories and constructive theories, theories that are built from the ground up, constructive theories, you specify the ingredients to build them up, versus principles theories where you lay out very general principles, desiderata, things you desire of your theory, either for reasons of intuition or that are empirically grounded, and you work down and ask what theories satisfy those desiderata. A lot of the theory of causation is done in the principles framework. People don't use that language for it, but they lay out general principles. Faithfulness, causal Markov condition, various things like that. Reichenbach's principle of common causes. And that's what Bell was trying to do in his Bell's theorem. And I think that's a mistake. Because we just don't have enough of a grapple on what causation is, especially for microphysical theories, that simply taking principles that we have heuristic reasons to trust for macroscale causation and then driving them all the way down to microscale and thinking they still work, I think is asking for trouble. What I'm doing here is building up what I mean by individual microphysical causal relationships constructively, and then asking what properties they satisfy. And in some cases, they will not satisfy things like faithfulness or the causal Markov condition, or even simple versions of Reichenbachian common cause. So I think in general, in this approach, you're not always going to get models that obey those kinds of principles.
Okay, I mean, I don't know really much about this principle, but I guess what I'm asking as well is, what does a correlation look like?
Well,
What would be is there a conditional, would there be a conditional probability connecting correlated variables?
in this case, B, C, and D are going to be correlated to A, right? You specify the, the A's by law has conditional probabilities that depend on B, C, and D. So this is exactly a case of correlation.
Okay.
Yeah.
So there's in this approach, there's like no notion that can you, because you open up the question of like, how do you distinguish correlation from causation?
Right.
So can you in this?
You can by proposing a theory, a model with arrows.
Okay.
So there's two questions here. There's the question of what causes are, and then there's the question of causal discovery. How do we go in the world and suss out these causal relationships? What we do is we can't see the arrows. The arrows aren't there to be seen any more than forces, Newtonian forces can be seen directly. What we do is we do lots of experiments and we look at correlations. And then what we want to do is build a causal model with arrows. And then it's an inverse problem. We're trying to find the causal model that best captures all the predictions, whose predictions best capture all the data. And if we have a proposal for a model, we have some very, very complicated experimental data on correlations of many, many variables. And I propose a simple model with arrows, and that model is correctly predicting all of those data that we're getting. Then this would be our proposal. And then on that theoretical proposal, on that model, we would say, okay, we have the following causal relationships. So the process of guessing the model is the causal discovery process. Once we have it, we then would read off that model what the causal relationships should be, but they're theory dependent. If someone comes along and says, I've got a different model that works even better with different arrows, then our proposal for what those arrows would be could be different. So an example would be, suppose you think that magic doesn't work. So suppose you think magic doesn't work. You can't say magical spells, they don't do anything. You say a magical spell, abracadabra, green apple will appear over there, and then a green apple happens to show up. Was that causal? Well, I mean, I'm not sure. Maybe you could study the situation, maybe do statistics on it, maybe you have, maybe every time you say it, an apple shows up, but maybe there's some hidden person listening in you, and maybe there's some other explanation. But in any event, you notice these correlations. You might be suspicious that these are causal just because your theory of physics doesn't include magic. But suppose someone comes along and says, oh, I'm Gandalf the Great. I actually exist, and magic really exists. And what you're saying is an ancient spell that really does conjure apples. Would you say, well, maybe actually this is a causal relationship? Maybe. But notice the facts didn't change, right? It's just that your theory changed. If your theory is one in which magical spells can non-locally produce apples, then the same facts now would have a causal tinge. And so I think this is what Everett meant when he said that without a theory, there's no notion of causation. The theory is what gives you a reason to say that there's a causal relationship between things. I think that microphysical causation is grounded in laws. Again, to be distinguished from causal discovery. To go out and find causal relationship doesn't always mean you have to have a model in mind. It's distinct from what causes are.
I'm so sorry, we're gonna have to kill this now, but if we could just thank those people one more time.
I'll float around. I'm happy to keep answering questions. I like talking to people.